Hello, everybody, and welcome to another episode of the Starts podcast. My name is Jagat.
And my name is Janak, and we're both co-hosts of the Starts podcast. Joining us today is Ankit Gupta. Ankit Gupta is the co-founder of Reverie Labs, a pharmaceutical company that aims to accelerate cancer drug discovery. Reverie Labs was acquired by Ginkgo Bioworks in 2024, and now Ankit serves as a visiting partner at YC, a leading venture capital firm that has cultivated some of the world's best companies, including Dropbox, Airbnb, and Coinbase.
All right, thank you so much for joining us today on the Starts podcast, Ankit. It's a true pleasure to have you here. How are you?
I'm doing great. Thanks so much for having me. Really excited to be here.
Great, thank you. Well, to kick off today's conversation, Jonik and I were both very inspired by your undergraduate research on using dilated CNNs to detect regulatory genomic elements from raw DNA itself. Can you tell us a bit more about your first exposure to sort of combining these fields of computation, biology, and chemistry? And, given today's sort of field of AI, how would you sort of approach this intersection differently if you could?
Yeah, I mean, it was you have to really rewind the clock here a little bit. So I was in college in 2013 to 2017, and this was during an era in which, basically every single week there was a new machine learning paper that came out with the new architecture, and people were kind of applying it to different domains, right? So like AlexNet came out right before I came to college, and then during college was a series of CNN papers like RCNN and mask RCNN for segmentation and semantic segmentation, NLP papers like seek-to-seek attention, and eventually attention is all you need, which was sort of the first transformer paper. Um, and then people were sort of increasingly in this mindset of how can I encode some amount of inductive bias into my model architecture and apply it to like an interesting data set of a relevant size and kind of use that to solve an interesting problem. And so I came mostly from a computer science background. I'm not like a real biologist. I took like a few bio classes in college or whatever, but a lot of my close friends were biologists in college. Like actually, if you look at like a photo from my wedding of like a lot of my college friends who were in my wedding party, like 9 out of 12 of them were uh, college friends of my wife and I who were like biologists, including my wife. And so many of us were sort of thinking about biology as like an interesting application area for quite a bit of time during college. And so naturally, when I sort of entered I think it was my junior year of college, when I started doing like kind of more serious machine learning research, I had taken a deep learning class with this guy, Sasha Rush, who is like a notable NLP researcher. And at this point at Harvard, I'd taken like one or two bio classes, but I was sort of thinking about this, what I knew from those classes and from, like AP Bio growing up, to kind of like map those onto what I knew about NLP. And what I knew about NLP is that a lot of models kind of struggled with long range dependencies at the time. And so like this was like a notable problem with seek to seek models where they have this kind of vanishing gradient problem and they have this like information bottleneck with the sort of central vector and a seek-to-seek model, and so with the kind of latent vector. And so the question was, if you start to expand these models beyond the relatively small context of what was at the time the relevant text tasks, which are much smaller than most of today's tasks, can these models actually generalize well? And then people were trying all sorts of different things to see how you could extend that. Like attention, it was all you need is sort of one approach to do it, using dilated convolutions inspired by a paper called WaveNet, which was for like audio generation, was another one. And so the thought was like, okay, what's like an interesting task I've been thinking about that's has this kind of long range dependency problem? And the thought was like, oh, DNA might be that, because just like intuitively, like DNA folds and it has this like long range dependency problem because things that are very far from each other in 1D space are close in 3D space. And so it was like, okay, can we actually like kind of capture those properties with these machine learning models? So it kind of came from just like basic intuitions about biology and then a lot of intuition about machine learning and trying to combine those together to find if a model would do well.
Yeah, and I've often heard people tend to say that, when you're in biology, it's harder to pivot to computer science as opposed to the other way around. Do you sort of agree with that view in terms of, um, like understanding which field to sort of like first gain exposure to sort of jump into the other field?
Yeah, I mean, I think that people with deep scientific backgrounds in any field have a lot of plasticities to move around. So I do think that like statements like that, while they are common and in some way I agree with it, like I think that's sort of like a relatively unfair generalization that people
Right.
often say. I do think what is true about computer science is that computer science is a broadly very useful vehicle for advancing to other topics. Like computer science teaches you deep logical thinking, it teaches you how to build things, it teaches you how to test hypotheses with code. And so that is just a very useful set of building blocks to then do lots of other things with. It's why a lot of computer scientists go become rocket designers or robotics people or bio people or chem people or whatever. And it's not because like bio people are like less smart to go the other way or something like that. It's just that it's like a much more useful foundation for jumping. It's a very useful foundation for jumping off. I don't know about very useful, but it's a broadly very useful foundation. And for me, I think what my general hypothesis has been, and like maybe people with PhDs would like disagree with me on this, but I think I'm right, is like with like a strong computer science background, the difference between you and like an expert in some other field is more like a month of focus than 5 years of a PhD. It's like you have like a relatively nimble brain that can go with focus and effort, can like learn quite a lot about another field, insofar as that expertise is useful for like starting a company or whatever. There isn't actually that much you usually have to learn.
Yeah, no, I think in my own personal experience, I've sort of found a sort of very similar journey. And I feel like computer science really has taught me to, sort of think unconventionally for maybe for lack of better words. And biology, on the other hand, has sort of like made me sort of question, like, can we do something else novel? Sort of how can we challenge the conventional literature, as you mentioned, like maybe using dilated CNNs.
Yeah,
So I feel like they both definitely are, sort of symbiotic in that way.
totally.
I also want to ask a question on like the evolution of like machine learning architectures in general.
Yeah.
Do you think that like, given that modern day transformers are like autoregressive in nature and that's how they're primarily used to like, generate words, do you think that we're kind of overfitting now, given the fact that we're using these autoregressive models to like model gene expression? So for example, like CZI recently released a tool called Transcriptformer where they autoregressively generate these like gene tokens and gene counts. And it's kind of pushing me to think about like some of the early days of biology where people were only using like simple classifiers to like, for example, as a case study, segment neurons. So I was wondering, would you say that we should take a step back or continue with the current LLMs?
Yeah, it's a really good question. I mean, I think that so okay, I have sort of two competing views here that I'll maybe frame that might be useful. One is that actually, if you look at the best models in a wide variety of biology tasks, they actually are encoding a lot of biological priors. Like my favorite paper, maybe of all time, is the AlphaFold 2 paper. And the reason it's one of my favorite papers of all time is it's actually like 10 machine learning papers combined. Like if you like read the paper and do a deep dive, it's basically like 10 NERPS papers that they like stapled together and made into a Nature paper. And each of those 10 things is like either a training trick or whatever, but mostly they're like various ways of encoding biological priors or physics priors into the model architecture, right? So you have like the like triangle inequality aspect of it, for example, is a great example of this. Now, it is true that in many ways we've sort of like taken that to a lot of extreme already with what we've done. And in many ways we are limited in those domains by often only being able to train on like one very neat data modality, right? You kind of have to have all your data look in one particular way to be able to train that way. So in like protein structure data, it's like these PDB files, for example. What is nice about this sort of like, okay, just kind of, like figure out a tokenization and then like YOLO train it with an LLM. What's kind of nice about that is that your bottleneck becomes, can you tokenize it? And in many ways, that's a nice sort of convenience factor, right? It's kind of like a nice, like, it's like in like an object-oriented programming model. It's like you have this object model now. Like if you can tokenize this, then everything else you can kind of factor away because you can just train auto-regressively. And that introduces certain advantages. You can now train on like these multimodal data sets. If you can combine everything into one tokenization format, you can prompt it in sort of interesting new ways because you can literally prompt these things in English often. I forgot how the exact model you mentioned worked, but I think often they have these sort of nice perks where there's often these questions of like, okay, if you have RF diffusion, for example, which is one of the former types of models, how do you actually prompt RF diffusion to like give you the thing you want? You can't like talk to it in English. You have to kind of, give it an input in a very particular format. And so there's certain benefits to that as well. And then finally, the nice benefit of transformers is that for some reason, it's rather hard to overfit transformers. Like literally just like to actually like create losses that start having the validation look up. For whatever reason, seems to be kind of hard to do this. I'm not sure there's like great literature on why, other than empirical literature that suggests it is. And that's also a really nice property. Like basically, if you look at the history of people doing machine learning from 2017 to 2022, what most machine learning people will tell you they spend most of their time doing is stopping their models from overfitting. And there's lots of tricks people that were invented to like help with this. And so that is a nice perk that you have to deal with that less. And so I'm of two minds about this. Like, I think, yes, we probably will need to encode a lot of biological priors to make really great models of complicated biology. Also, there are certain perks to not doing that or to perhaps only doing that in the context of these autoaggressive models. And so I think there's probably going to be some amount of work that's happening in both. And I will say, like, if you look at some of the best models coming out, like if you look at like the Boltz model or like Chai's models or whatever, like these models these are like both protein relevant models and kind of small molecule protein binding models. they seem to encode quite a lot of biological prior. They're not just like tokenize and put it into an LLM. They're doing quite a lot of interesting kind of physics modeling in the models themselves.
Yeah, that's pretty cool. And I think that the fact that like a lot of genetic information fundamentally is just, language, like it's just letters that can be like quite similarly input into like a very natural language field
Yeah,
makes it quite conducive for like transformers.
yeah.
But I still kind of find myself a little bit skeptical on like whether or not we can treat like, traditional syntax to be the same when it comes to like genomic information. But as you mentioned, I think biological priors does hold like a lot of rich
I mean,
context.
particularly challenging because you have really noisy information of this
Yeah,
genetic information,
that's
right? Like,
true.
okay, it's one thing to just have like DNA sequence alone, but any kind of functional readout on DNA, like if you have, like which pieces of DNA were expressed, like that's a very
Yeah.
noisy readout you're getting. And yeah, you can't quite think of it, or at least it seems naive to quite think of it as just like words and sentences in the way that we think of, English words and sentences. It's not quite the same thing.
Yeah. So our next question for you is also, around computer science and computer science skills. Given the fact that, CS as a major has become like increasingly popular across, many colleges, and it's also like a reliable prerequisite for learning how to, think and become a technical founder and engineer as well. Would you say there's any other skills or domains that people tend to overlook, such as math, physics, that they should value when it comes to, creating a startup?
Yeah, I mean that's a really good question. I mean, there's no doubt that I think computer science is the single biggest one, and like even in the era of AI and whatever, like I still think computer science is like an incredible foundation for how to think well. I do think that the types of computer science, the aspects of computer science that are most useful as a computer science education, this might be like a somewhat hot take, is like to me it is not the actual software engineering parts of it. Like it's not the like I know how to do object-oriented programming or whatever. Like, I mean, that's useful
Yeah.
too, but like you can kind of just like, read a couple blog posts and figure it out. Um, it's the like deep algorithmic thinking. It's being able to break down a complicated problem into its subproblems. I actually really personally quite like systems programming because there's something like I can't quite put my finger on it, but there's something about like really knowing how a computer actually works. Like the first time I like had to decode assembly and understand exactly what was happening, there was like something that clicked in my brain of like, okay, I actually get this, and maybe it's just like a confidence thing. I don't know if it's actually practically that useful, but it gives a lot of kind of inherent value. Operating systems very similarly. So I think there's like the elements of a computer science education that I think are most useful are basically the confidence aspects of really knowing how a computer works. So like things like systems programming, and then the like theoretical aspects that are really more like math and stat. They're really like a proof-based math class slash like linear algebra slash number theory slash probability theory. Like those are probably the set of things. This is more for being like a machine learning type of engineer, I suppose. Those last two things. To me, those are the things I think back on all the time. Like I think about this class called Stat 110 in college. That was like an intro to probability class. I think about Stat 110 all the time when I was running my company. There's like lots of relevant things in there, much more so than, most of my CS classes.
Yeah, I did also read like when in one of your blogs online, you mentioned that when you're running Ribery Labs, a lot of those Harvard CS classes were skills that you're using, at Ribery and also like when you transition to Ginkgo. So I was curious, is that like if you could give us like a case example of like what algorithmic thinking you use and like where it applied in like biological data or yeah,
Oh yeah, there was a lot of these. This is one of the things where I was like, oh wow, these classes were actually pretty useful. So like a
yeah.
quintessential example of this is in chemistry, there's this, or slash in chemical representations, there's this concept of a ECFP, an electronic connectivity fingerprint. It's basically a way of like representing a molecule in a fixed size vector. And like it has this like fancy formula and whatever. And like, if you actually look at how an ECFP works, I don't know if have you guys seen this before, this ECFP concept or how it works. Okay, very simple. You take a molecular structure. So imagine a molecular structure, like classic thing from like AP chemistry or whatever. And then you take every point in that. I'm oversimplifying here, but basically it's like you take every node in that, meaning every atom. You look at the things it's connected to, so the within some radius, and you hash that. And then you take that hashed thing and you store it in a vector, and you do that for all sets of things. And this is called an electronic connectivity fingerprint. It is also called a Bloom filter. If you've taken like a probabilistic data structures class, it's just a Bloom filter. And so, I mean, it's a Bloom filter with a very particular hash function. And what's nice about this is like, if you're trying to do really large scale like vector search or lookups on a large set of ECFPs, which is what we would do at Reverie, we would have like billions of these we want to do searches against. if you're thinking like computer scientist, you look at that and you notice that and you're like, oh wait, I can just use like any Bloom filter library and this works really, really well. And there's libraries that can do Bloom filter lookups at like trillion scale. And so this was like the type of thing where it's like, had I not taken that class, if I wouldn't have noticed this and like thought to Google, like, is ECFP just a Bloom filter? And like found some random Reddit post that said it was the same thing and like confirmed my thinking and then like went and used it. So that's like one example of it. Another example of it is a lot of the work we did in synthetic molecular design. So actually like taking molecules and then designing variants of them. A lot of that is basically like assorted tree search and graph search kind of stuff. I mean, there's like lots of variants of this, but like as a simple example, there's a task in chemistry called retrosynthetic planning. And so that's basically like take a molecule and figure out the set of reactants that and reactions that you can run to create that molecule. And this is useful because you want to like take a molecule that your thing generates, your AI thing generates, and determine whether you can actually synthesize it with the building blocks you have sitting on the shelf and the reactions you know how to run. And like long story short, this is basically just depth first search with some heuristics. In fact, it is so simply that we actually made that into one of our interview questions for computer science hires, where like the trick was basically like, can you map this to DFS and then implement DFS? And uh, I think like that's the type of like kind of algorithmic thinking that I'm not saying is like unique to computer scientists. Like obviously chemists do this stuff too, but it's like very natural to computer scientists to think of these problems that way.
Yeah, it's interesting to see how like a lot of like foundational thinking can be applied in various domains. It's almost like a toolkit for the world and like how to
Yeah.
think about things. I think like a couple months ago, I was touring like I want to say a semiconductor lab, and they were applying like very basic electrical engineering concepts to like manipulate heat to use it for like some biological application.
Totally.
So yeah, it's quite exciting to
No,
see like yeah.
yeah, exactly. And especially that particular like kind of computer science toolkit, like being able to think algorithmically, being able to think about data structures and algorithms, like these are just like so useful for some like the whole world runs on data structures and algorithms, right? And so it like ends up applying to all sorts of different domains.
Yeah.
Yeah.
I think speaking of classes, I don't know if it's just me, but I feel like the number of people who are dropping out to make companies sort of is like exponentially increasing. And so I wanted to ask, what are your thoughts on these young YC founders or founders in general, dropping out or not dropping out that are making companies they aren't, particularly domain experts in? What are your thoughts on sort of, these AI tools sort of representing PhD level knowledge and using these as sort of guides or aids to reach product market fit or make a successful company.
Yeah, so why don't I kind of split that into two parts? One is sort of this like young people starting companies with that require domain expertise element, and then like sort of separately this question about dropping out specifically, because I think that's like a somewhat more complicated thing. But I
Right.
want to talk about both things.
Sure.
So the first thing, I think this is like probably the best time in history for young people to start companies, and this is for a few reasons. One is that it used to be, and for a while it kind of was, that like for like most of the last decade that you kind of needed to have some level of domain understanding about something to know that there was a problem worth solving, right? It was like, I worked at a company that had problem X and I built an internal tool for it. And so now I'm going to go build a company that makes that internal tool for everyone. That was like a very classic story of a lot of great companies. And this made great companies. Um, what's interesting right now is like two things are happening in parallel. One is like basically the entire development stack of how software is made is being rewritten with AI. And that means that essentially every dev tool company is like potentially compatible with. And it means that there's a whole bunch of new dev tools to be built. Like an entire new development stack is going to be built over the next few years. And so that's why we see a lot of incredible new dev tools being made. And the people who are most native to that stack are the young people. It's people who grew up with ChatGPT, who grew up with using tools like Cursor and Windsurf, who think very intuitively about what it means to have AI generated code and where it would work and what issues they would have. It's much more likely that a 22-year-old notices those things correctly than like a 32-year-old or a 42-year-old. And so in many ways, young people just have a straight up advantage. So that kind of that's one component of it. And the second component of it is that increasingly the speed at which you can get an idea to from your brain into code that works into a customer that's using it, that is basically exponentially sped up, right? That's like 20 years or 10 years ago or 20 years ago. 20 years ago, that was probably like, I don't know, like a month or something like that, or 3 or 4 weeks. Like take like half a YC batch just to like make your first prototype. In my era, it was probably like a week or something where you could like, like write a whole piece of software, like, like a B2B SaaS tool kind of thing and like get something that someone will actually use. And today it's probably like a day, like, or maybe like a few hours where you could like conceive of an idea and make it well enough. I'm not saying like a perfectly polished product, but well enough that someone could reasonably be like, I want to buy that. or at least reasonably like put in their credentials, sign into it, use it, and give you feedback on it. And what that means is that for founders, you can get an incredible amount of feedback from the market. And I think one of like our biggest sort of like startup pieces of wisdom has been that it's actually very hard to like preconceive great startup ideas. Great startup ideas are much more likely to be encountered than preconceived. Like it's very hard to just like from first principles be like, this is a great idea. And so if you can kind of get your ideas to the market faster and you can kind of build with others, um, it is much more likely that you encounter great ideas, even if your first idea is kind of crappy. And that is a very kind of counterintuitive aspect of the current way of building things, which is basically you should just start shipping and start building with customers and getting feedback on it. And what that means is that the delta between a young person and an older quote unquote experienced person is way lower, right? If you can just get the same experience by just shipping a few times, you don't need 10 years of, like industry experience or whatever. That's a huge advantage. And then young people have another advantage, which they tend to just like have more time, right? They tend to not have as many other things going on in their life that very reasonably affect someone's time later in life. And that ends up the sum of those things ends up being an incredible advantage for younger people. And so it's just a great time for young people to start companies. And I think it's why we see so many young people starting them. Now, on the dropout point, like I think I'm a little careful about that. I want to be a little careful about this. Like I generally think that like college is great for most people. And like I personally never felt much desire to drop out. And I don't like push people to drop out of college. Like I think for most people, they should just like do college. And honestly, they should probably start a company like right after college. That's like probably the optimal time to start a company for most people. I think what is a very sensible thing to do while in college is to work on interesting side projects. And a project is defined in this very particular way, where it's two people that are technical, that are building something and getting someone else who's not their friend to use it. If you define a project that way. And like, I think which is interesting because like you can kind of do a computer science education at a place like Stanford and never do a project where like everything is either solo or no one else uses it or it's assigned to you by at an internship. Oh yeah, that's the other thing. It can't be assigned to you. It has to be of your own volition. And like as a result, it's actually often rare you see people do projects. And I would say like the optimal way to run school is like do projects by that definition, and then let your project pull you out of school if it must. Like I think the idea of like going to school just to drop out, like for the brand or whatever, I think that's like kind of lame and like not what I would recommend. But I think if like a project genuinely pulls you out of school where you're like, oh my God, like why on earth am I in school? Like I should be doing this thing and making it a real thing. Like, yeah, sure, obviously, like that's great. But I wouldn't like advise people to drop out.
Yeah, no, that totally makes sense. I think I feel people often look at it sort of in the reverse way, and that, oh, I need to like make something really big and drop out, and now is the time to make a startup. But I feel like the more authentic and intrinsic way is just to sort of obsessively follow whatever you're interested in, and if nature sort of lends its way to going full time on a startup, then I think that's sort of the more successfully natural way, in my opinion.
Yeah.
Um, yeah, and I was also curious as you were mentioning sort of, these AI tools, sort of using them to, compete with other companies. Do you even think that, with these like Cursor or Windsurf or like Replit, for instance, that people nowadays, and I say this because we've seen a couple successful solo founders as well. Do you even think people, truly do need a co-founder? And I guess to that end, as sort of as a side question, how did you end up meeting your co-founders for
Yeah,
Revry, and
totally.
what intrinsically do you think led to that successful sort of like launch of the company?
Yeah, totally. Great questions. On the first, I would say mostly yes. And that's mostly because having a co-founder has very little to do with the like labor of the job. I mean, some of it is that. Like there's just a lot of stuff to do. So it's nice to have two people instead of one, but you could just have like a founding engineer or something to do the labor of the job. Um, it has more to do with the kind of decision fatigue and emotional regulation needed of the job, right? Like the funny thing about doing a startup is that inherent to the assumption of building something new is you have to convince yourself that what you're building is the right thing to build. And often you have to tolerate like an absurd amount of rejection, right? Like 95% of people that you pitch this new thing to are going to be like, yeah, like go F yourself. Like this is dumb. No.
Yeah.
And you have to somehow still have the arrogance to believe that you're right. And most people very naturally, when 19 out of 20 people they talk to say go F yourself, like are not inclined to continue working on that thing. But most great startup ideas start that way, where like, like take like DoorDash, like almost every like potential user and every investor told them to go F themselves. And they were correct, it turns out, right? And that's where having other people that you trust to get kind of shared conviction either on doubling down on something or pivoting away from something ends up being really, really important. So like there's a level of just like you have to make like 10,000 decisions a year as a founder, and you just want to like not get fatigued by that. And two, you have to make these very challenging decisions around counterintuitive things, and it's very hard to do, very hard to convince yourself to do that solo. It often helps to have someone you think is is just as great as you be on the same page as you. It can be very reassuring to be like, I'm not an idiot, like I'm not a crazy person, like I'm doing a sensible thing. Maybe someday like people will trust ChatGPT so much that that'll be the case. If I had to guess today, you could like very easily tell ChatGPT to like like it'd be very hard to like have true trust in it because you can kind of like prompt it to like either agree with you or disagree with you very easily, right? Whereas you can't really do that to like your best friend. And so generally, I think that's like the biggest value to having a co-founder. And in terms of how I met my co-founder, Jonah was was like with me to the very end. He and I were like randomly assigned freshman entryway mates in college. So like we were in the same freshman entryway. We took most of the same CS classes in school. Honestly, our resumes were like nearly like you could almost like swap each other's names on them and they'd be like sort of correct. We interned at the same internship our second year. So it was like a lot of overlapping experiences. We did like, if you go back to my GitHub, you see like 10 projects he and I did together in college. So we had a lot of reps on assorted building stuff together, mostly for like class projects and some personal stuff. And so it was a very natural person for me to build something with because it was just someone I trusted a lot.
Yeah, I really like how you mentioned the theme of conviction. This is something that both Jonik and I really found. It's something that people bring up sort of in a sense somewhat frequently, and you can sort of think it's cliche. But I often think that, whatever is cliche truly is, it's said for a reason. And this is
Yeah.
what Sam Altman mentioned during the first like opening talk at YC Startup School,
Yeah.
having conviction. And I think one more prime example, from DoorDash or like a different company would be Canva.
Yeah.
The number of rejections that the founder faced, and then ultimately, she successfully developed her own company. To me, it's like very, very surprising. You sort of have to be rationally delusional in some manner to to a degree where you firmly believe in what you can do. Um, and
Exactly.
yeah, and I think to that point, my question is, for a lot of young people, I feel in today's generation with a lot of noise, it can often be a bit difficult to build that conviction.
Yeah.
Uh, so my question is, how would you sort of recommend? And I feel like this also could not be a question because I feel like every individual develops conviction in their own sort of unique pathway.
Yeah.
But if you were to advise maybe a young individual on some given advice to build conviction, what advice would you give to that individual?
Yeah, totally. Well, so maybe I'll start with what advice I wouldn't give, and then I'll
Sure.
switch to what I would give. The
Yeah.
one I wouldn't give is like to work with someone with quote unquote very complementary skills as you. Like, I think this is like classic bad startup advice is like, oh, I'm a technical person and I don't really like talking to users. Let me go get a non-technical co-founder who like is a sales guy. Or not that like all salespeople can't be great founders, but it's like most likely the person who you're going to get conviction with is going to be someone who you speak the same language of as and you like have a shared camaraderie with. It's like it's why a lot of brothers actually start companies together, right? It's like or siblings start a lot of companies together is that you like literally speak the same language and like grew up from the same roots. And I think that leads to a lot of shared ability to create conviction. I think it's a really important thing. And so, yeah, probably find someone a lot like yourself, especially if you're like a technical person another person who's like a good friend of yours from a similar language, probably a good way to do it. And then in terms of how you actually, for a particular idea, get conviction, it's mostly like don't treat it like a theoretical exercise, right? Like it is an empirical science, right? It is not a like startup building is not a theoretical science for almost all startups. For almost all of them, it is a series of hypotheses you have that you then run experiments on to collect data about. And those experiments usually involve building something and getting someone to pay for it and their willingness to pay and how they respond to it and how much they do or how much they use it are the pieces of data you get that tell you what the next hypothesis to run is. And I think that like kind of scientific method framing of it often can like push people out of their comfort zone also because it's like, oh no, I actually have to like get someone to buy this thing for me to know that it's a good idea. I'm not gonna be sure. Like there's no certainty in this. It is just a set of hypotheses that I have to design an experiment for. But like what's good is like a lot of computer scientists are actually very good at designing experiments, right? That's like, actually a thing that computer science teaches you, or like science teaches you. And so if you can convert that instinct into an experiment, like that's the kind of hard part, but that's also how you get conviction is to be like, okay, yeah, like I don't even really know why people want this, but like objectively they do. And so that's a good sign. Like let me now try to like tease that out and figure out where to go from there.
Yeah.
Yeah. So another question I also want to ask is like more diving into the pharma world and like a lot of the intricacies that I really enjoyed reading on your blog. And one of them was the fact that you began to note that software is more like a bottoms up total addressable market where you have to look at it from a perspective where you're selling something to like an X amount of people for a Y price and a Y cost and like profit margin. And then realizing that looking at like pharmaceuticals and like drugs from a top down perspective allows you to get more revenue and is more profitable in the long term. So I was curious to know what did the transition for Reverie Labs look like going from something from like a software idea, especially you coming from like an NLP background, to eventually like a molecule as a service company to fully integrating everything from like bottom to top.
Yeah, totally. I mean, so just to clarify that bottoms up versus top down thing, what I was getting at there is that people often delude themselves into thinking that their market is big by thinking of it in a top down perspective. They'll be like, this market
Yeah.
spends $1 trillion and I can make it 1% better. Therefore, I deserve 1% of a trillion. Therefore, that's $10 billion. Like, oh my God, what an incredible market. But in reality, that's just like not how things work. In reality, it's much more reasonable to think about things in a bottoms up perspective, which is like, I think I can sell this thing 1,000 to 1,000 people, and they're willing to pay $100 each, and so therefore my total market is 100,000, which would not be very big. And so I think on what I was getting at there is that a lot of people delude themselves into thinking that there's an incredible opportunity in something, especially in something like pharma early stage software. And obviously there are some big companies there, but mostly they often find themselves kind of surprised because they see it as this market that spends like an insane amount of money on hundreds of billions of dollars on R&D, but like actually the willingness to spend on software is extremely low. And like that is one of the early realizations we had as we were trying to sell software during YC when we were in YC in winter 18 is like very quickly we were like, oh shit, we thought they would be willing to pay like millions of dollars for this, and actually they're willing to pay like tens of thousands. And so we're like off by an order of 100x there. And what that means is, and like maybe if we were less naive, like we would have just known. But like to my point, that was like a month of focus that we figured that out in. And then we sort of morphed ourselves into saying like, okay, how do we actually capture the thing they want to buy? And the thing they want to buy is actual molecules. And so we have to kind of be in the business of making our own molecules, potentially taking on more technical risk and kind of scientific risk, but then ultimately developing those. And so we sort of morphed from the software business to first one that was doing these bio partnerships with pharma, and then ultimately running our own therapeutics programs ourselves and looking to out-license those drugs, during clinical development.
Could you walk us through internally what like maybe some of the conversations you had within the company as you were like, shifting from a software to like a more like fully vertically integrated company?
Well, I mean, truthfully, I think the latter was kind of the original dream. We just maybe didn't think that we would be allowed to do it. Like, I think to be totally honest, like, yeah, we wanted to build like the next Roche or the next Genentech. Like that's kind of the dream. It wasn't to like make this like rinky-dink software thing. But the assumption was, oh, we're like two 22-year-olds, we're computer scientists. Like, surely the only thing we're going to get funded for is making software. Turns out not really. Turns out people are actually like very willing to allow young people to like take a bigger bet and take on technical risk in exchange for much, much, much bigger outcome. Like that actually, the venture math actually works better for that. And so that was actually one of the things our YC partners pushed us on is like, maybe you should actually just like do the thing you actually want to do. And, we'll figure out the way to like, monetize along the way so that like, you have some revenue stream and so on. Like there's a bunch of, logic to how you do it. But like often this is like a counterintuitive thing about company building is like the harder thing is actually easier to fund because the opportunity, if it succeeds, is like way, way, way bigger.
Actually, also, yeah, on that note, I also want to point out something about like young founders also building in like the computational bias space. One thing I've noticed is the fact that like a lot of key values and like the main company value does come from like in-house data, which is kind of hard to garner as like a young person in college, just writing code or software. So I was curious, do you think that like companies that are purely based on software that tend to like agentically automize or agentically automate like traditional biological workflows or just add like another piece of software in like a pharmaceuticals company's workflow are like the best way to go? Or is it such that at the end of the day, most of these companies will end up kind of having to do things on their own, mainly because like there's a lot of other intricacies which I read, like these pharma companies will give you more of their harder tasks, which they don't want to deal with. So yeah.
Yeah, it's definitely quite tricky. I mean, so one of the things that's notable is that it is true that having internal data is a very often very important part of building like a great especially in any kind of machine learning business in life sciences. It is also true that it doesn't mean you have to run your own lab, right? Often you can use outsourced lab providers to actually relatively cheaply get access to a good amount of data if the kind of data you're looking for is a relatively commoditized assay. So in our case, we were doing like small molecule binding. We actually never operated like a physical lab that we had our logo on. Like we always use these they're called contract research organizations where, we would tell them what to do, how to do it, what the protocol is. Like we were like, like puppeteering them, but it was not our lab, which means we didn't have to do the millions of dollars of upfront to set it up. And that has certain advantages. Even a very early company, you can get things going. Unfortunately, in exchange for a slower speed relative to doing it yourself. So there are some disadvantages too. I will say, like, in terms of the types of companies that need any kind of like interesting internal data, it does vary. Like, I think there is this new generation that you pointed out to of like, kind of, as you call it, agentic kind of science companies where, truthfully, I think most of them are still figuring out what the business model there is. But, if the very basic business model is let's either augment or supplement or replace human labor, in some like relatively generalized way in some lab function with an AI agent, well, there's actually a relatively simple pricing model there. The question is like, can you actually do that in science? Like, does there exist a science task that is sufficiently kind of replaceable with an AI agent, right? As opposed to, let's say, like legal intake receptionist or something like that, which is like basically someone who answers the phone and like talks to you about what your legal problem is and then like fills out a form. Like you can imagine that's very AI replaceable. Like you can kind of do the whole job with AI. Whereas with science, it's not actually as easy to think about what the like full job is that can be directly replaced. There might be some ones that I'm just not thinking of right now, but like probably to the extent those exist, those are like near-term scientific kind of company opportunities. Often it's more like fitting an AI tool into an existing workflow and not necessarily like supplanting labor. That often is like harder to price. And I think there's lots of new startups that are experimenting with this and figuring out different parts of the drug discovery stack in which there's opportunities to sell. Like actually in clinical medicine, there's a lot more interesting kind of business models that we could talk about if you're curious than in preclinical medicine. So I think a lot of companies are actually looking over there. But I think this is very much TBD on like what works here. There's going to be a lot of experimentation that happens.
Mhm. Yeah, would you be like as a follow, would you be able to talk also about like the business model that Chai Discovery eventually went with? I'm mainly curious behind that just
Actually
because
don't
I
know what their current business model is. I assume they're
okay.
doing some kind of partnership thing or maybe
Yeah.
making some drugs. I know originally, I don't want to speak just about Chai, but I think a lot of
Mhm.
companies started with like kind of like a token-based, like access to our models type pricing, like similar to like OpenAI and stuff. I'm not sure I've seen any that have quite gotten that to like really work. There's one company called Tamarind Bio that offers like open source models as a service that I think seems to be working really well. I'm not actually that familiar with exactly what Chai's current business model is. I know more about just like their public model releases and stuff.
Oh, okay. I was only wondering primarily because I think I heard that the first tool they built was only using public data to like build the foundation model off of that. It was just
Yeah.
like it kind of stands out from a lot of pharma companies where like you have to like rely on in-house data. But yeah.
Yeah, I mean, I think the question is what data is the tool used for, right? Like, if I recall, the original model is used primarily for like binding and folding. Interesting problems, but they're
Mhm.
like two of many, many, many problems that matter in drug discovery. And often the other problems that matter involve like labeled data that you might not have sitting in the public domain. Something like, predicting small molecule solubility. There's like very little small molecule solubility data in the public domain or predicting its membrane permeability or something like that. So often for these unlabeled or like semi-supervised type of tasks, like public data is really good. Like protein folding is a great example of this, where yeah, it's labeled in that there's like structures, but there isn't like kind of functional readouts of the protein. And often for these functional tasks, it's quite hard to get enough public data. And so I would love it. Like it would be amazing in my mind if
Right.
like the NIH spent $5 or $10 billion and just like labeled a ton of data. I think it'd be one of the best things for pharmaceutical industry is for like a public effort to do so. But for now, it mostly doesn't exist and is like in some weird fragmented set of a lot of different pharma company databases. And even so, it's just not that big. The amount of data that's probably in all the pharma companies combined is still probably a very small subset of what is needed.
Right.
I'm also curious more so about the partnerships angle and sort of what your philosophy on partnerships is more broadly with with Revving Labs. And if I recall correctly, it took 18 months to go from a promising side of partnership to an actual signed deal. Um, And the question is, at what sort of point did you know you're ready, to pitch some given value for a partnership? And I ask that because, the drug discovery field is, of course, a very uncertain and can be, a very long and difficult sort of pipeline.
Yeah.
Uh, and so I'm curious to know if it was sort of more like on a computational end, like we have really good QED scores or like very viable drug candidates, or more so, we've tested these in the lab and they're actually, have very minimal downstream effects or other, complications that are in the field.
I think there's a few things to think about here. One is that fundamentally doing a partnership, whether in pharma or any other field, it is just enterprise sales, right? And when you're doing enterprise sales, what you have to care about is basically like who are the people I am selling to, right? And this is different from who is the company I am selling to. People often think about sales as I'm providing value to a company. And that is true, I suppose. But companies are just compositions of people, and you have to think about sales in the context of which people am I providing value to? Which person is going to get promoted if I succeed in this partnership? Which person is going to lose less sleep at night? Which person is going to like bring a lot of value to their team and actually really care about that? Um, that is somewhat different from which company should broadly be buying my product. And so often you have to kind of treat the exercise, this is something we talk about at YC quite a lot, as like a detective mission, right? You're like a detective who has to like understand the like inner like functioning of this weird giant behemoth entity that actually has a bunch of subsets that all kind of hate each other, and you have to find like who's got what willingness to spend on what and what each person's okay or like objectives and key results are, OKRs are, what are their like goals that they're trying to achieve, and then how can I slot into those? And so I would say like the process of approaching that partnership is much like any other enterprise sale, and that's kind of the game you're ultimately playing there. And that's why it takes a long time. It doesn't just take a long time because it's like hard, but it's because like sometimes you have to like navigate through a maze to find the right set of people to actually be working with and have the timing appropriately work. There's not actually 18 months of stuff to do. There's like, I don't know, like a couple weeks of stuff to do, but you have to kind of like get to the right people to do the couple of weeks of stuff with and be at the right time.
Yeah.
What I will say about these partnerships is like maybe this is like the piece of advice that's like most anti the like broader biotech conventional wisdom is that partnerships probably like slow down your company progress. They probably are not going to be what makes you a $1 billion company because it's very hard to capture the upside in them. They're probably like in many ways a quote unquote waste of time. They're also like probably the only way for most biotech companies to be default alive versus default dead. And I can define what that word means in a second if you're not familiar. And being default alive is one of the most important things for an early stage startup to do. Um, and like default alive, what that fundamentally means is that your revenue growth rate is sufficiently high such that if you like take what your burn looks like over time, the area under that curve is less than your cash in bank, right? And so for most like software companies being default alive, like if you look at a company like Anthropic, like it burns a ton of money, but I would bet you if you look at Anthropic's growth rate relative to their cash in bank and their current burn, and they actually are probably default alive right now. And all companies start default dead. And most biotech companies are default dead until the day they IPO, and actually way past that, right? They're usually like always dependent on venture dollars to be able to fuel money into their system because they make no revenue. They have no way to make revenue, and they have no attempt to make revenue. They have no desire to make revenue. But the beautiful thing about becoming default alive is you no longer, as a company, need venture dollars. You probably want venture dollars, and venture dollars can be valuable and provide like a fuel and allow you optionality and so on, but you don't need them. And that change from want to need is like a fundamental freer for founders and is like super counter the biotech advice because it probably means that your company is going to grow slower and it doesn't match the 10-year fund cycle and blah, blah, blah. But like as a founder, like that's someone else's problem, not yours. And as a founder, it's like really important to adopt this philosophy that is very common in the tech industry and very uncommon in the biotech industry to like first be default alive. And that's one of the most valuable aspects of doing these partnerships. You can actually get quite a bit of revenue and make it so that, if the market tanks like it did over the last few years, you don't need immediate venture dollars to survive and you can actually have a lot of optionality.
So effectively, it can be, in a sense, a double-edged sword where, a partnership could leave somebody default alive or default dead. But I guess the key, as you mentioned, sort of is like decomposing and understanding how exactly can you meet somebody that, can partner with your own mission or your own goals, to keep the company running, essentially.
Exactly. And often
That's a
that
very
is something
open
that's like
hypothesis.
a little tangential from the primary mission. And in most companies, it is not worth doing things that are tangential from the primary mission, right? Because it's like, well, you gotta stay focused. And so I understand that general instinct. But in a lot of bio companies, the tangential things can make you default alive. And like if that is what the tangential thing buys you, not just like curiosity or whatever, but like something that allows you to be default alive, like that's actually a really important thing to at least very strongly consider. And I think the conventional wisdom kind of says just like stay on the primary thing only. And that's probably good for the investors because they make 20 bets and they only need one to work. But it's not necessarily great for the founders where they want to be that one out of the 20 that works.
Got it. Yeah.
I want to point out also like another issue like in the field of data when it comes to like building a pharma company, and this is something that I also noticed that as somebody who's done research in the field for a couple of years, is the fact that like a lot of these models, as you mentioned, Ankit, it's the fact that like AlphaFold and DiffDock don't really like they're not like a panacea in a sense, and the
Yeah.
fact relies in the fact sorry, it lies in the fact that we need like admin data to really accelerate things or make a difference because they can run like a lot of assays which can cost them like a lot of money, but we don't really have much rich pharmacological data that can address this issue. So it's
Yeah.
curious to see like where you see this issue going in the next decade or so.
Yeah.
Yeah.
And you know when I that particular line of reasoning I apply mostly to small molecules, which is the part of biology I have the most, or part of drug discovery I have the most experience in. I think in biologics it's a slightly different set of constraints where actually like binding along unlocks quite a bit. There are certain other equivalent tasks like thermostability and whatnot that are I think in many ways easier tasks than like some of the small molecule tasks. But I think just for simplicity, let's like focus here on small molecules for a second, which is like the biggest class of drugs. Um, yeah, I mean, I think this is like a massive challenge with small molecule drug discovery. And I think there are a few companies that are kind of going after ways to address this. There's a company called Axiom Bio, for example, that's making models to predict toxicity, which is kind of getting at this exact problem. I don't know the details of how far they've gotten or anything like that, but I think it's at least like an admirable goal. It like makes sense as a problem to try to solve. If I had to guess, the very well funded labs that are working on this type of stuff, like Isomorphic, which is the DeepMind spin out, or Zera Therapeutics, who I think is mostly working on antibodies, not small molecules, but still, like, if I had to guess, they're probably going to spend a lot of money on generating lots of data for these tasks in which the public domain data is pretty bad. But I think this is challenging, right? It's quite hard to be like, if I had to be totally honest, if you said like, hey, Ankit, what's the right way to spend like $10 billion on making a drug company? It's probably like spend 9.7 billion of it on making data and then like zero point 0.3 billion of it on making a bunch of drugs. And but that is like very hard, obviously, for a company to actually culturally do. It's like an awkward thing to ask your investors for. It's like a culturally difficult thing to actually do. You have to make a bunch of bets that may or may not pay off. But probably it is going to look something like that for it to actually work. I don't know enough about how these companies work internally because they're very private to like actually know that that's going to happen. But it is probably going to be a like relatively intense ratio to that effect. And like this kind of thing happens in tech, right? If you look at how Anthropic or OpenAI spend their dollars, it's basically all on data and compute and like a small amount on like people, and that's essentially it. And I think that it's like possible for pharma companies to do this too. I just think historically they don't. And so TBD on what that actually means, but I think that's probably what's necessary to make it in small molecules really work. I think in antibodies and other biologics, there's a version of that that also needs to happen. I suspect the order of magnitude and amount of data needed is somewhat different, but I don't actually know the exact numbers that it would take.
Do you think the notion of like a virtual cell where like we're able to go from this unperturbed like basal cell state to like the perturbed cell state after like like an intervention, whether it's like chemical or small molecule or antibody, would in a sense solve this issue because it would, give us a lens to like whether or not it would affect the cell's toxicity levels or like just cell damage in general? Or would you say we would still have to go down the traditional like ad path?
I think you need both. Like the virtual cell
Okay.
stuff is really cool. And I think most importantly, it's really cool for biology broadly. Like I'm glad it's happening in places like the Arc Institute where it's like open science and it's going to be released to the world and so on, because it's, I think, great for target discovery and for, broadly understanding biology, maybe to some degree understanding tox. But like the vast majority of tox issues that happen is I find it very hard to believe that a virtual cell model is going to be able to
Mm.
suss that out. I mean, they're often like a weird multifactorial aspect of things. They're often involved whether certain molecules get piped into certain parts of the body and whether they bind to a certain thing well or not enough that affects that. We don't even have great physical models for half of this thing. So if you half of this stuff, so if you look at like MDCK, which is one of the like membrane proteins that things bind to like get through, like I don't think we even have a great physical model for MDCK in terms of like if you do a simulation of what it's doing. And so maybe there's, but like my point is like it's quite hard to even have all the great physical models of doing this. That makes me not really buy that the virtual cell alone gives you that. But like, yeah, no doubt, like it's a great direction of science, and I think it makes total sense to do like large scale perturbation-based data set generation. Probably especially to the extent people can do that on human-derived data. Like I think there's a company called Noetic that does a version of this. Also,
Yeah.
Ginkgo Bioworks does a version of this. Several other companies do too, in which you're actually perturbing like kind of human-derived data. That I think is like particularly exciting and interesting, but I don't think it's alone a panacea. It's like one of many things that are necessary. None of these things also tell you how like soluble a small molecule is,
Yeah.
or
It's true.
like how broadly, brain penetrant it is, for example.
Yeah. Yeah.
And to add on with, as mentioned before, the drug discovery being a very timely and cost-consuming process, how far do you think we are from, having AI models that can sort of incorporate multiple data modalities, whether it's like, personalized patient data and maybe within even seconds or minutes generate health reports that indicate the right drug that we should develop for the patient itself? Because right now, I feel like most existing literature or labs are focusing on, how can we develop the drug to specifically target, a given disease as opposed to what is the right drug for a given disease and the patient's sort of biological profile.
Yeah, I mean, I think what's challenging about that is not the like AI model component. Like I buy that an AI model could probably do that today as well as like a human could look at that and look at things. The problem is that the question is, do you need it to be superhuman or just human level? Let's assume you need it to just be human level for it to be useful, because that's very hard for me to predict what it would take for something to be superhuman because we don't have like a great way to eval that. But like let's say it's just human level. Even for at a human level, it's quite hard beyond things that have clear genetic biomarkers to be able to know that a particular like readout you would get in a patient report should be mapped to a particular drug that exists out there. There are a bunch of companies thinking about this and like incorporating new data modalities. I think it's like a potentially really exciting use case of proteomics, for example, where you can actually use like, the instinct being like protein levels or like maybe a better indicator of kind of like clinical relevance than like pure genetics. And so perhaps like you can use, blood, like plasma proteomic levels or something like that to like determine which patients to enroll for what trials or which drugs to give them or something to that effect. Like, it's probably a lot of different variants of this basic idea space, but this is obviously like a pretty big idea space. And that to me intuitively makes sense, but it's like the hard part there is like someone needs to go like take a lot of proteomics data and like figure out like appropriate science that like tells you that certain levels are associated with certain disease states for like every disease state. And I totally buy that AI is going to help us do all that kind of science faster, but I think like that needs to be established first. Like that doesn't exist in the literature for like every single disease such that a great AI model could just know what those relationships are. And I don't think those relationships are one of those things that are like you could just like assemble them from ground truths and like the model could just kind of like figure it out. It's kind of just like an empirical thing. Like a lot of these mechanisms we don't really know. And so I think for a while it's going to be like an interesting kind of like underlying, kind of like proteomics and whatever other data modality science problem to like figure out what those relationships are. Once those are then mapped out in the literature really nicely, yeah, I totally buy that an AI agent could like look at a panel and like know things about targets or like certain like signatures of like higher or lower expression of certain things that like a human could not reasonably memorize every single one. And so it makes sense that you would use like an AI tool to use that. But we kind of first need to know what those things are in the first place. At least that's my instinct. I'm not really an expert in that.
Yeah, and on the other side of the spectrum, what are your thoughts on sort of letting AI, completely automate this, like I guess for health reports, for instance. And I asked that primarily because, we're discussing the fact that AI can hallucinate or, provide inaccurate decisions or make mistakes when you're dealing with, very critical sort of like health sensitive data as well.
So are you referring to like do the job of a doctor, like do diagnosis and like that kind of thing?
Yeah, effectively. Or if there's a better sort of, I guess, hybrid approach of having the doctor intervene with the AI, I guess what would you sort of envision might be, the most ideal uh,
Yeah.
partnership?
I actually don't think the like hallucination thing is that big a deal, to be totally honest. Like, yeah, okay, there's hallucinations and whatever, sure. And I'm not saying like we should all go use AI models today, but it seems very improbable to me that in like on the order of like 1 or 2 years even, there's going to be like a meaningful hallucination problem as like the primary issue with these models. To me, the primary issue with these models is the following, is that like my general philosophy on AI models is that we have to, if we want to incorporate AI in our life, we have to understand its utility in the context of the human world we already live in, right? It's not in some like simulated artificial world. It's in like with the specific constraints of the human world we live in, which means that we need to eval these models under the specific constraints of the human world we live in. And I think this is like a big, big area of like missed opportunity. And actually, if you talk to like people at places like OpenAI and whatnot, they will say like we have saturated every benchmark that's out there. We need better benchmarks, and people are working on harder benchmarks. Things like the newest ones that models are being evaled on. And in something like medicine, this is like a really important nuance, right? Like we have for a while had models that can like beat doctors at the USMLE or whatever. And even recently, Microsoft put out this thing of like iterative diagnosis where the model can like, they call it like pathomedical superintelligence, where like the model can request an exam and then you'll get the score and the model will decide what to do with that and request another exam on a patient and it'll do this iteratively, kind of more like a doctor. But
Mhm.
what that's missing, even in that example, is like it's missing the real nuance of like how a doctor extracts information out of a patient. The way the Microsoft thing works is it uses these New England Journal of Medicine write-ups, which are like perfect idealized stories that a doctor has already synthesized. But that like does the hard part of what a doctor does, which is like hear, what a patient says, of which like a huge fraction of it is like irrelevant or like, a misrepresentation of the truth or something they're embarrassed to tell about, or maybe like incorrect, or they're not able to fully describe their pain, or they don't speak the language very clearly, or they don't remember things fully. And then in there's lots of nuggets of truth also. And like a doctor, an experienced diagnostician, can like extract the relevant things from that and like know what to even do. That's a really hard problem in itself.
Yeah.
And we don't have a great benchmark for that. And so like my general thinking about like how to bring AI systems into this world, my question for how long it takes to do that is basically the answer to that is as long as it takes to design that benchmark. Like I'm pretty sure our tools with RLHF can do really well on essentially any benchmark we design. But designing a benchmark like that is a pain in the butt. Like it's really hard. Like I'm not claiming that's going to be easy by any means, but that's probably what it's going to take is like some kind of software engineer slash doctor collaboration. And
Yeah.
maybe a place like Microsoft is suited to do this. They have doctors on their team, but like to really represent what that collaboration looks like, to really represent what the realities of the underlying raw data in the world looks like, not like some fictional reality, but like the actual reality. And if we can make a really good benchmark for that, yeah, I bet like relatively quickly we will do really well at that benchmark. I think that's what the
Yeah.
last few years of benchmark building has shown.
Yeah, this is something I've been thinking quite deeply about recently, actually. And I wonder, like, is this sort of like a benchmark of empathy in a way, and sort of understanding, what exactly the patient might be, needing, as opposed to sort of just like directly feeding all this factual information into the model? Um,
I think that's a really nice way to think about it. And like what's hard about it though is that you like how that empathy comes out. It's not just like the patient spits stuff at you for 10 minutes and then you say you like extract out the parts you understood, right?
right.
There's a conversation, there's a rapport that happens. And so
Yeah.
you need a benchmark in which like the the like AI system is like saying things to probably like a real patient, and then the patient is like responding is probably a real way somehow, and there's some sort of like iterative feedback that happens there. You could probably do this through some kind of like teacher forcing algorithm if you guys are familiar with this kind of stuff, where it's kind of like how the Tesla autopilot like ghost mode works. At least I think how it
Okay.
works. Where basically it's like running a model in the background while a real person is driving, and like basically the diff between what the real person did and what the model would have done is like the training loop. Probably there's going to be something to that effect that it takes to actually like RLHF these things in practice. But it's still hard to know exactly what the underlying benchmark would be in which you could actually like talk this thing to a real person and like see if you can extract information out of it, unless someone can like build a great AI model of a patient. And maybe that's what it takes is like you have like great models that represent different archetypes of people with very high accuracy. I don't actually really know how you do that, but to the
Yeah.
extent you can do that, that might be a way you kind of build this benchmark.
Yeah. And I could be wrong, but I feel also data is inherently like, in a sense, the fundamental, like limiting factor, if you will, just because, people inherently are changing over time as well. And
Yeah.
so I guess you have to consistently fine tune, some given model to humanity's, change. But yeah.
Yeah, and like you probably need to somehow have that data like ambiently generated by humanity, right? Like the
Yeah.
internet is a great way we can do this, and why LLMs do well on stuff that there's internet data on, because the internet's just like constantly generating ambient information about how the world works, and you can just keep training on it, or RLHFing it or whatever. For like things that largely don't happen on the internet, like how people interface with doctors, this is like quite hard actually, like to like create the like ambient information. And like now we have like mics and stuff in some doctor's office, so like maybe we could start to do this, but like it becomes a whole like regulatory complicated thing in itself. And so there's like some practical constraints that make some of these things pretty hard to do, but I think that's probably what the future is going to look like to do it.
So you also talk about this analogy of like coin flips and like coin mints and how like the farmer world is like very much dependent on like successful coin flips.
Yeah.
And I was curious to know your thoughts on like, primarily like software companies like Evolutionary Scale, like where their main, at least so far, their main advancement has been like ESM3 and like how ESM embeddings are kind of like, revolutionizing almost a lot of other machine learning models too.
Yeah.
So what are your thoughts on such software-based companies? And do you think that these companies, in the end will eventually kind of be like their own Roche or Genentech, or are we seeing a different form of trajectory like in today's age?
I mean, look, I really want to believe that it's possible for Evolutionary Scale or a company like it to make all of its money. And you should probably like ask Alex Reeves what the plan is there. I don't
Yeah.
really, but like I would love for them to be able to build a giant profitable business selling just software. Like I think that would be great. Like it would be an amazing thing for the industry. But if you just like do the basic math on people's willingness to spend on software, it seems like it would be improbable to do that unless you could make the pie of people willing to buy that way, way, way bigger, unless you can like dramatically increase people's willingness to buy. That is possible. People do build things that increase people's willingness to buy those things. Like something like Nvidia is a good example of this, right? Where like people can only even do things, or like TSMC, right? TSMC like basically like created the market that it supplies. And so like it is possible to do that. But it is, I think, does seem improbable that with the current market size of buyers, that there exists like a sufficiently massive software return for a company that's raised like whatever insane amount of money they've raised. Now, what they do have is a lot of cash, and what's nice about that cash is you can use that cash to start making some coin flips. You can start saying like, okay, we have all this tech that apparently is great, like let's use it to make some drugs. And if you have like whatever, I don't know how much they have, like let's say about 200 million bucks, well, that's like enough money for like 5 or 6 coin flips of like molecules to the clinic, if not more. And so, or I mean, it depends on which molecules they do, but this on the cheaper side, it's probably around that many. And so that's enough coin flips where, you might actually be able to prove that you can get a much better than normal kind of success rate and like kind of be in a position to succeed. But it's somewhat hard to like know if that's actually going to work for them. It's also possible they go down some path of doing lots of partnerships. That would be pretty reasonable too, from my like become default alive framework. The challenge of partnerships is very unlikely they're going to capture the kind of clinical stage upside of those partnerships. So it's very hard to build like $1 billion business doing that. But it does let you get a bunch of revenue that might let them stay default alive long enough to like figure something out. So I don't know for sure. Like I don't want to speak for them. I
Hmm.
think they're like very smart people that clearly like have raised a lot of money for a reason. I'm sure they're like up to interesting things, but yeah, like it seems like the pure software, like just sell tokens math, like doesn't really make that much sense to me. But like I totally buy that that could be a way of like getting distribution, for example, to like lots of different people for relatively little money, and then like kind of upselling them with some kind of partnership or like clinical opportunity. So like there might be some like secondary strategy they're taking that isn't purely revenue generating.
Yeah, definitely. I also want to talk about like some of the more tractable problems in healthcare right now that young founders and builders can work on.
Yeah.
You did mention that like target discovery, trial design, and like recruiting the right patients are
Yeah.
more important than finding, necessarily like the right drug against a known target. And I was curious to know like what are some like the most pressing issues in these areas right now that are quite conducive to work on.
Yeah, I mean, one of the things to know about, like an interesting kind of reality of clinical discovery is that almost all dollars in drug discovery are spent on clinical trials, right? Like the vast majority of them are spent after phase one begins. And so just naturally, there's going to be more opportunity to do things there. And there's also interestingly more parties to sell things to, right? There's like insurance companies, there's providers, there's clinical research sites, there's pharma companies themselves, there's the regulatory people on both sides of the regulatory table. So there's lots of parties that could be potential buyers of whatever you're doing. Not to mention like bankers and investors and stuff like that. And what that means is that it kind of opens up the surface of types of software one could build. There's also this nice, benefit of like when you are, if you can accelerate a drug trial, it has actually a relatively nice and easy to price value, right? It's basically you take the peak sales of the drug, you divide that by number of days of patent life remaining, which any drug that's in clinical trials already been patented, which means there's a patent cliff, which means you can figure out the patent life that remains. So if you take the peak sales divided by patent life, and then you multiply that by probability of success at that moment, that basically gives you the probability of approval at that moment. So that'll go up from like 10% to 90% as you go from phase one to phase three. That basically gives you a very simple EV calculation of the value of 1 day of time saving. And it turns out that number is really high. It can be like $1 million a day or more. For a lot of like relatively large indication area drugs. So it means that if you can like prove that you can accelerate a trial by like even a day or two, people should be willing to pay you like on the order of millions of dollars for that. And obviously there are ways to probably accelerate trials a lot more than a day or two. And so this just like ends up being a kind of surprisingly large surface by which you can build a service business or a software as a service business to do interesting things. And so I think that's like actually a quite exciting domain in which one could, work on interesting things. Surabhi Sarna, a former YC partner, started a company focused on regulatory document writing, probably based on this like very similar philosophy of like if you can speed up this thing that takes forever, which is like writing regulatory docs, which like obviously AI can do pretty well, then you can perhaps save quite a bit of money doing it. I'm not sure exactly what she's up to these days, but like that was I think the original idea at least. And so that's one of those domains actually there's lots of interesting things where yeah you have to kind of dig in and understand how that world works, but to my point earlier that might actually be easier than you think as a relatively young person, and you can actually like sell software for a relatively large amount of money relatively quickly. And so I think that's generally a pretty fruitful place to explore. I wouldn't say people shouldn't explore preclinical medicine. I mean, there's lots of great medicines to be made too, and people should keep doing that. But there's sort of like this stuff is like the non-sexy stuff, right? Like it's not hard to convince an ambitious young person at Stanford or whatever that they should like work on drug design because drug design is obviously sick. Like it's awesome, right? You get to think about physics and chemistry and whatever. This stuff is like regulatory document writing. It's like hella boring, but it's actually sort of conversely might have like much bigger opportunities one can capitalize on much earlier. And so, it's like one of those things to like not close your mind to that early. And I honestly, I wish I had thought about it earlier.
Hmm. How do you go about like kind of staying like cautious about the fact that there's still like regulatory implications like in the clinical trial process where like like I assume that a lot of the time being spent in clinical trials is and waiting on like approval on drugs for like the next stage, and some of these like hurdles are like kind of like written and embedded in laws. So how would you, I guess, go about? I mean, is there any way to overcome them from like an entrepreneurial standpoint?
Yeah, I mean, honestly, I don't know that that ends up being that much of an issue for companies that are there because especially when they are selling to someone else that is subject to that, it means that, yeah, okay, there are regulatory hurdles, but like that's really just a matter of like convincing the counterparty, who's usually the one actually subject to those, that you are a trusted actor, right? That you're not going to screw things up for them, right? And
Yeah.
so it's true that you have to demonstrate that you're not like full of, like that you're not lying or that you're going to be serious. And like you have to kind of like be mature about it. But fundamentally, that's not that different from them buying any other software that might be supporting them, right? Them trusting Slack is not going to lose their data, or them trusting another software provider won't, mess with their underlying technology. And so I think it's one of those things where you do have to like present yourself carefully, but ironically, if you're a service provider to that, you're not actually directly really subjecting yourself to that kind of regulatory burden necessarily, or at least not in a way that is like particularly distinct compared to like, starting Robinhood or starting Kalshi or like a bank or one of these other areas where there's like regulatory risk.
Yeah, definitely.
Great. Well, thank you very much for joining us today, Ankit. We greatly enjoyed learning about your journey with Reverie Labs at YC and as well as your research in computational biology.
Absolutely. It was a lot of fun, guys.
Thank you so much.
Thank you very much.
Thank you.